We thought we had solved one of the universe's greatest secrets. Through our observations, we learned that in our galaxy alone, there are over 400 billion planets. This was a triumph, but it was the very achievement that blinded us. Because the existence of trillions of planets was meaningless. If the gravitational constant had been different by just 1%, none of them could have ever formed. Physicists speak of 10 to the power of 500 possibilities that make our universe possible. All other probabilities meant emptiness, chaos, or an instantaneous collapse. The fact that atoms do not disintegrate, that stars do not explode. Was it all a coincidence? But what's truly unsettling is that the existence of this fine-tuning might point to a structure larger than the universe itself. If you too are wondering why our universe is an impossible exception, then hit the like button and subscribe, because in a moment, you will be standing on the edge of nothingness. We are beginning. For years, we believed in certain rules about how the universe works. We thought that galaxies formed slowly, that stars were born in a specific rhythm, and that the conditions required for life were extremely rare. The Milky Way was a standard template of the universe for us, an orderly, predictable place where everything worked as it should. That's why, when searching for life elsewhere, we always looked for places similar to our own. Calm, middle-aged galaxies, stars similar to our Sunday. But James Webb looked into the depths of space, and everything changed. When those first images began to arrive, we understood that we would have to rewrite the books that explained the rules of the universe. Because Webb didn't just find new planets or distant galaxies, it found structures that should not exist. Therefore, we must begin with one of our most fundamental assumptions about the universe: galactic uniformity. Our galaxy, the Milky Way, is a massive spiral containing about 100 billion stars. For years, we assumed that galaxies like this were the cosmic norm. But that's like looking at a single tree in a forest and thinking all the world's forests are the same. Webb showed us that every galaxy is a completely different experiment with its own set of physical rules. Each of the more than 2 trillion galaxies shining in the observable universe tells a unique story of how matter can organize itself over billions of years. Some create stars at a frantic pace, at rates hundreds of times greater than the Milky Way's star production rate. These starburst galaxies flood their surroundings with a torrent of ultraviolet radiation, intense enough to strip the atmospheres from young worlds in seconds. In contrast, galaxies like our neighbor Andromeda form stars at a much slower pace, about 1/3 of our galaxy's rate. This creates a much calmer radiation field in its disk regions. Why does this matter? Because it proves that a galaxy's life-bearing potential cannot be defined by a single recipe. The conditions we know as calm may not be a universal requirement. Perhaps life is born in the most chaotic, most violent environments, adapting to rules we can't even imagine. But what's truly surprising is where these differences emerge. This brings us to our second fundamental concept, the galactic habitable zone. Just like the Goldilocks zone around a star, it was believed that galaxies also had a supposed belt where life was viable. You couldn't be too close to the galactic center because the star density there is too high. Supernovae exploding every few million years, and the immense gravity of the central supermassive black hole destabilize planetary systems. The radiation levels are more than enough to sterilize surfaces. Likewise, you couldn't be on the far edges of the galaxy because these areas are devoid of the heavy elements needed to form planets and life. Therefore, it was thought that life could only exist in this safe middle belt. But Webb's findings are shattering this neat map. The telescope is finding traces of complex molecules critical for life, precisely where they shouldn't be, in the most chaotic, most radiation-filled centers of galaxies. Even in the oldest and most distant galaxies, where heavy elements were thought to be extremely scarce. This suggests that the habitable zone is not a static belt, but perhaps a dynamic area that constantly changes throughout a galaxy's history. A region might be dangerous for billions of years, but then, for a short period, maybe just a few 100 million years, it could become a perfect sanctuary for life to take root. This increases the number of potential life-bearing locations in the universe by trillions, because we now have to look not just in the safe suburbs, but also in the most dangerous city centers. Therefore, if our rules about where life can emerge are wrong, our rules about under what conditions it can emerge may also be wrong. This is where the third and perhaps most disruptive concept comes into play: star types and life. According to the Standard Model, the best candidate for life is a G-type star like the Sunday. It emits a steady energy for billions of years, is predictable, and allows planets to develop a stable climate. In contrast, red dwarfs, which make up about 75% of the stars in the universe, were generally seen as poor candidates. Because these small, cool stars, especially when young, experience violent flares that could scorch planets in their orbits. Moreover, planets orbiting them closely become tidally locked, one face perpetually turned towards the star, while the other remains in an eternal darkness and cold. However, Webb began to study the atmospheres of planets orbiting these unfavorable red dwarfs, and it overturned our expectations once again. It is finding traces of water vapor and other chemicals essential for life on these planets. How can this be possible? Perhaps tidal locking creates powerful winds that help distribute heat around the planet. Perhaps those violent flares, instead of destroying life, are triggering the chemical reactions needed for it to begin. This possibility pushes the number of potential worlds in the universe beyond our imagination. Because for every sun-like star, there are about 15 red dwarfs. If even a small fraction of these stars can host life, then the number of potentially life-bearing worlds in our galaxy could jump from tens of billions to hundreds of billions. All of this leads us to a single conclusion. Galaxies have different rules. Habitable zones are much more diverse than we thought, and the wrong stars might actually be the right places. But behind all these discoveries lies a deeper, more unsettling truth. These structures that Webb has found don't just contradict our current theories, they challenge the age of the universe itself. It seemed impossible for such a young universe to build such complex and massive structures so quickly. Therefore, we must put aside everything we know and ask, if the rules of the universe are not as we thought, what was it that allowed these giant, early structures to exist? What was it? Because the answer we were looking for was not in a single galaxy or a single star system. The answer was hidden in the architecture of the universe itself, in its structure on the largest scales. And when we understand this structure, we are forced to confront the fact that life is not just possible, but perhaps inevitable. Therefore, we must first return to the most basic question: what is orbiting in these galaxies? The answer is our fourth concept, the principle of planetary abundance. For years, we thought Earth was a special place. We believed that a rocky, water-bearing planet of the right size was like winning a cosmic lottery. But even our own research in the Milky Way has demolished this idea, because planets are not rare. They are a standard byproduct of star formation. It seems that almost every star we observe has at least one planet in orbit, and many host entire families of worlds more diverse than we could ever imagine. This is a fundamental law of physics that applies everywhere, from our neighbor Andromeda to the most distant galaxies. Therefore, just in our local group, our small cosmic neighborhood of a few dozen galaxies like the Milky Way, Andromeda, and Triangulum, there are, by a conservative estimate, trillions of planets. The vast majority of these planets will undoubtedly be cold, barren, or unstable. But this number is so astronomical that even a small percentage means an unimaginable number of potential worlds. In the Milky Way alone, the number of Earth-like rocky planets in the habitable zone is estimated to be 40 billion. Why is this important? Because this transforms the search for life from a needle in a haystack problem to a game of statistical certainty. If you have trillions of chances, it becomes almost impossible for the universe not to succeed at least a few times. Life is not a rare jewel. Perhaps it's an inevitable chemical outcome. But where these planets exist is at least as important as their number. This brings us to the fifth and largest scale concept, the cosmic web. We think of the universe as a soup of individual galaxies. But this is completely wrong. On larger scales, the universe resembles a gigantic web. Galaxies are strung along the threads of this web. We call these threads filaments. Where these filaments intersect, massive cosmic cities called galaxy clusters are formed. And between these structures stretch enormous cosmic voids that are almost entirely empty. Each of these structures creates a completely different living environment for the planets within it. For example, a galaxy cluster, like the Virgo cluster, is a chaotic place where thousands of galaxies are packed together, just a few million light years apart. The intergalactic medium here is filled with a 100 million degrees Celsius plasma emitting high-energy X-rays. Galaxies frequently collide. Their star formation processes are violently triggered or completely halted. It is extremely difficult for life to find long-term stability in such a place. In contrast, the filaments stretching for hundreds of millions of light years are more stable environments. The galaxies here are not as crowded as in clusters, but they are not as isolated as in the voids. Therefore, they can have a continuous flow of gas to form stars, but they are not subjected to the constant destructive interactions from their neighbors. And what about the cosmic voids? The galaxies in these vast, dark regions are the loneliest places in the universe. They live in quiet isolation, millions of light years away from their nearest neighbors. This tranquility might offer a perfect environment for planets to evolve undisturbed for billions of years. But it comes at a price. These galaxies are often poorer in heavy elements. This can limit the formation of complex rocky planets. Why is this important? Because it shows that a planet's fate depends not only on its star or its own galaxy, but also on where it is in the universe. Is life better nourished by the intense energy of a cluster, the balance of a filament, or the silent isolation of a void? We do not yet know the answer to this question. We now know that galaxies have different rules, that safe zones might be an illusion, that the most common types of stars might be the best places for life, that the universe is filled with trillions of planets, and that the fate of all these worlds depends on their location within a giant cosmic web. Our theoretical framework has completely changed. Our old maps are now useless. Our understanding of the universe is much broader, much more complex, and much more hopeful than it was just a few years ago. But theories only go so far. The real question is this: in this universe full of new rules, what does the James Webb Telescope actually see when it looks out there? What is the concrete evidence that supports these theories? In those first unsettling images, what exactly were those structures, hidden in the light of the cosmic dawn, that defied the laws of physics? It is now time to stop speculating and look at the real discoveries. Because what Webb has shown us is even more astonishing than all these theories. And now comes the real shock. Because theoretical possibilities are one thing, but the reality, frozen in the oldest light of the universe, is something else entirely. When Webb turned its eyes to the cosmic dawn, it didn't just upend our expectations. It tore up our physics book and showed us a completely new universe. Here is what it found. Let's start with the first anomaly: the galaxies that shouldn't be there. They simply should not have existed, but they were there, glimmering in a period of time just 300 to 500 million years after the birth of the universe. This is just the first 3% of the 13.8 billion year cosmic history. According to the standard model of cosmology, galaxies in this era were supposed to be small, irregular, and filled with young, blue stars. They were meant to be the first seeds that would build larger structures. But That's not what Webb saw. It saw fully fledged giants, galaxies as massive as the Milky Way, or even 10 times more massive, with billions, even tens of billions of solar masses. What was even more shocking was that these galaxies already contained old, red stars. This was like a baby being born and looking 40 years old. Because these galaxies weren't just big, they were mature. This seemed impossible. The standard lambda CDM model predicted that galaxies formed through a bottom-up process, where small structures merge over billions of years. There was simply not enough time for these massive structures to form so early. The laws of physics did not allow matter to assemble that quickly. When astronomers first saw the data, they thought it was a mistake, perhaps a calibration issue with the telescope. But the data was checked again and again, and the result did not change. Those galaxies were there, and they were challenging our most fundamental theories about how the universe began. But this was only the beginning, because at the center of these giant galaxies, something even more impossible was hiding. A monster, literally breaking the rules of physics. An overgrown, supermassive black hole. Existing just 700 million years after the Big Bang, this object had already reached a mass of more than 1 billion times that of the Sunday. This alone is astonishing. But the real impossibility was its growth rate. There is a physical limit to how fast a black hole can accrete matter. It's called the Eddington limit. This is the equilibrium point where the radiation pressure of the infalling matter prevents more matter from falling in. It's a cosmic speed limit, but this black hole, found by Webb, was exceeding this speed limit by at least 5 times. It's as if a car's theoretical top speed is 200 kilometers per hour, and you see it going 1,000 kilometers per hour. How could this be possible? For a black hole to grow this large, it would either have to start as a seed black hole from a collapsing star and have been accreting matter continuously with an impossible efficiency ever since. Or we have to assume that black holes form through a completely different, unproven mechanism called direct collapse. Therefore, this discovery didn't just find one weird object. It made us question our entire understanding of how the universe's most mysterious objects are born. There wasn't enough time. Known physics didn't allow it. But that monster was there. And then came the structure. Not just mass, order. The early universe was expected to be a chaotic, violent place. A place where everything was constantly colliding, merging, and being torn apart. Therefore, we didn't expect to find complex and orderly structures in the first galaxies. But Webb found traces of highly ordered structures like ring galaxies. Even more surprisingly, it found evidence for the existence of complex chemistry within the first billion years. Molecules like polycyclic aromatic hydrocarbons, or PAHs. These are essentially cosmic soot and are usually formed from the ashes of dying stars. Finding them this early completely wound forward the clock of the universe's chemical evolution. This meant that the basic components necessary for life might have been spread throughout the universe billions of years earlier than we thought. Therefore, the first galaxies were not just large and mature, they were also surprisingly complex and chemically rich. Massive galaxies, black holes exceeding the speed limit, unexpected chemical richness and order. These are not isolated anomalies. They are parts of an interconnected pattern, a pattern that shows the early period of the universe was much faster, much more efficient, and much more complex than our theories predicted. These findings force us to ask the question, how? 2. How did galaxies grow so fast? How did black holes defy the laws of physics? How did this complex chemistry emerge so early? Therefore, scientists are now forced to put even the most radical possibilities on the table, because the only thing that could explain these anomalies is the fact that our understanding of one of the universe's most fundamental components may be completely wrong. Therefore, scientists must now confront their most radical suspicions. What if that invisible web that forms the skeleton of the universe, dark matter, doesn't behave as we thought. Because what Webb has found are not just the strange behaviors of a few galaxies. They point to a fundamental misunderstanding on the largest cosmic scales. This brings us to the fourth, and perhaps most mind-boggling discovery, the premature cosmic web. According to our theories, the first galaxies in the early universe should have been isolated and lonely islands. Gravity needed billions of years to assemble them into massive filaments and clusters. But when Webb looked back to just 830 million years after the Big Bang, it didn't see lonely islands. It saw the beginnings of a cosmic metropolis, a massive structure, gravitationally bound, consisting of dozens of galaxies, a proto-cluster. The galaxies within this structure were only a few million light-years apart from each other, a stone's throw on cosmic scales. This structure spanned an area of more than 30 million light-years. This should not have happened. In that era of the universe, not enough time had passed to bring so many large galaxies together. This is like finding a map of a giant empire in the earliest days of human history, when villages didn't even exist yet. This structure shows that galaxies matured not just individually, but collectively, much faster than we expected. Because this means the clustering speed of dark matter must have been orders of magnitude more efficient than our standard model predicted. But no matter how fast a structure forms, you need bricks to build it. And where did these bricks, the stars, come from? This is where the fifth discovery comes in, the unstoppable star factories. It was a puzzle not only that early galaxies were large, but also that they were incredibly active. Webb discovered that many of these galaxies were producing hundreds, and in some cases, over 1,000 new stars per year. Let's put this into perspective. Our Milky Way galaxy, in its current quiet period, produces an average of only 1 to 2 new stars per year. So, these first galaxies were like a star production line, operating 500 times more efficiently than ours. This situation challenged known theories of star formation because when so many large, bright, and hot stars form simultaneously in a galaxy, the intense radiation and powerful stellar winds they create should have blown away the remaining gas into space, self-regulating and stopping star formation. This is called stellar feedback and is expected to act as a kind of thermostat that regulates a galaxy's growth. But the thermostat of these galaxies was broken. The feedback mechanism wasn't working. Somehow, they managed to retain the gas within them and continued to convert it into stars with astonishing efficiency at a rate of almost 90%. These galaxies weren't just large, they were greedy. And this greed could explain how the universe filled up with so many large stars, heavy elements, and thus the potential for life so early on. All this hyper-fast growth, massive structures, and unstoppable production inevitably point to a violent environment. And with its sixth discovery, Webb showed us the evidence of this violence, the ghosts of collisions. According to the standard model, major galaxy mergers should have peaked in the universe's middle age, about 6 to 8 billion years ago. But Webb found traces of massive galaxy collisions and mergers when the universe was not even 1 billion years old. Not just simple collisions. It saw giant systems in the final stages of a merger, their shapes distorted, spewing tidal tails hundreds of thousands of light years long. Within these tails, new star formation regions were shining, triggered by the shockwaves of the collision. This implies that the distribution of matter in the first moments after the Big Bang must have been much more clumpy and irregular than the models we derived from looking at the cosmic microwave background. Many more large structures than we thought were much closer to each other from the very beginning. Therefore, the early universe wasn't just a place of rapid growth. It was an incredibly violent place of constant mergers and collisions, impossibly large galaxies, black holes breaking the speed limits of physics, prematurely formed cosmic webs, unstoppable star factories, and early, violent collisions. When these findings come together, they tell us one single story. The early universe was a completely different place from our calm, slowly evolving model. Everything was faster, bigger, more efficient, and more violent. But these revolutionary discoveries would be meaningless without the incredible technology that made them all possible. So, how does this machine work? How does the James Webb Space Telescope capture this ghostly light from 13 billion light-years away, analyze it, and present us with the rewritten history of the universe? Because without understanding the engineering marvels at the heart of this incredible device, we cannot fully grasp the depth of this new and shocking story it is telling us. Everything is hidden in the perfect alignment of those 18 hexagonal mirrors and the incredibly sensitive technology that lies behind them. And this technology is not just hardware. It is a machine that rewinds time itself, using the most fundamental principles of physics. So, how exactly does this technology work? Let's now set aside the excitement and delve into the depths of the engineering and physics that made these incredible discoveries possible. Because Webb's secret lies not just in being a large mirror, but in our understanding of what that mirror sees, how it sees, and why. It all starts with the most fundamental nature of light. Therefore, first, we must understand the telescope's most critical capability, its window into the infrared universe. Imagine a distant friend throwing a red ball to you, but you and your friend are moving away from each other at an incredible speed. When the ball reaches you, its color is no longer bright red, but a darker red, or even an invisible color. This is what the expansion of the universe does to light. It's called cosmological redshift. The light from the first galaxies that formed shortly after the Big Bang has been traveling through the universe towards us for over 13.5 billion years. During this immense journey, because the universe is constantly expanding, the wavelength of light also stretches, just like a rubber band being pulled. Therefore, the bright, visible, and ultraviolet light emitted by those first stars is no longer in the visible spectrum when it reaches us. It has lost its energy and shifted deep into the infrared spectrum. Telescopes like Hubble, which operate primarily in visible light, cannot see this first light. They are effectively blind to it. But James Webb was designed for this exact purpose. Its instruments can detect wavelengths about 100 times longer than the reddest light the human eye can see, a range from about 0.6 to 28.5 micrometers. Why is this so effective? Because this ability gives Webb the power of a time machine. It's not just looking far out into space. It is looking back in time to that dark, mysterious era when the universe was only a few 100 million years old. It shows us a universe that Hubble could not see. But to see this faint, distant light is not just about looking at the right wavelength. You also need to collect an incredible amount of light. This brings us to the second technical marvel, the 6.5-meter golden mirror. A telescope's power is essentially determined by its light-collecting area, the size of its mirror. Webb's primary mirror is 6.5 meters in diameter. This is a light-collecting area, about 6.25 times larger than Hubble's 2.4-meter mirror. This is like using a giant swimming pool instead of a small bucket to collect water in a rainstorm. A larger area means more photons, which means more information, end quote. But it's not just its size that makes this mirror so special. It is composed of 18 hexagonal segments made of beryllium. Beryllium was chosen because it is an extremely light, yet incredibly stiff metal. This is critical for it to maintain its shape in the freezing cold of space, and the surface of these segments is coated with an incredibly thin layer of gold, only 100 nanometers thick. Why is gold important? Because gold is nearly perfect at reflecting infrared light. It reflects 99% of incoming infrared photons, ensuring that not even the slightest bit of light is lost. These 18 segments can move with a precision of 1/10,000th of a human hair, thanks to 7 small motors. Therefore, after the telescope was launched into space, folded up like an origami, these segments aligned themselves to form a single, giant, and flawless mirror surface. This engineering marvel is the key to Webb's ability to collect that incredibly faint light from a galaxy 13.5 billion light-years away. However, if you are trying to detect infrared light from the coldest and most distant objects in the universe, you have another major enemy: heat. The heat radiating from yourself. This requires us to understand the third and most critical technical detail: operating near absolute zero. Infrared radiation is basically heat. Therefore, if the telescope itself is warm, its own heat would completely overwhelm the signal of the distant galaxies it is trying to observe. This is like trying to listen to a whisper with a jet engine running next to you. To solve this problem, Webb had to remain incredibly cold. To block the heat from the Sun, Earth, and Moon, engineers designed a massive 5-layer sunshield the size of a tennis court. Each layer, made of a special material called capton, is as thin as a human hair. But these 5 layers create an incredible temperature difference between the sun-facing side of the telescope and the mirror side that remains in darkness. The sunny side heats up to about 85 degrees Celsius, while the cold side, where the mirrors are, is kept at -233 degrees Celsius, just 40 degrees above absolute zero. This massive temperature difference is a gradient of about 300 degrees. Some instruments, like MIRI, the mid-infrared instrument, need to be even colder. Therefore, MIRI has its own special cryocooler system. This system cools it down to just 7 degrees above absolute zero, which is -266 degrees Celsius. This extreme coldness ensures that Webb's detectors are free from thermal noise called dark current. This allows it to clearly detect even the faintest, most distant signals. Therefore, Webb is not just a powerful eye, it is the coldest eye in the universe. Infrared vision to see red-shifted light, a giant, gold-coated mirror to collect this light, and an operating temperature near absolute zero to separate the signal from the noise. These 3 fundamental principles form the basis of Webb's technical power. But this is only about collecting the light. The real magic begins when this light enters the telescope and is broken down by incredibly advanced scientific instruments. Because Webb doesn't just take beautiful pictures, it interrogates the light itself. And this interrogation is done with a technique called spectroscopy, which tells us the secrets of those distant worlds, their chemistry, their temperatures, and their movements. And how this spectroscopy works on Webb is the real key that unlocks the secrets of the universe. Therefore, we must understand Webb's 4th key technology, its spectrographs, the barcode scanners of the universe. At a supermarket checkout, a laser reads a product's barcode and instantly transfers all information about that product to the system. Spectroscopy does exactly that, but on a cosmic scale. When light from a galaxy or a planet's atmosphere passes through a prism, it splits into its colors like a rainbow. But this rainbow is not smooth. It has black lines where specific colors are missing, or emission lines where specific colors are brighter. These lines are the fingerprints left by the chemical elements in the gas that the light passed through. Each element absorbs or emits light with its own unique pattern of lines, just like a barcode. Webb's instruments, like NIRSpec, the Near-Infrared Spectrograph, and MIRI, are designed to read these cosmic barcodes with incredible precision. NIRSpec can take the spectra of more than 100 different galaxies at the same time. This is possible thanks to a microshutter array consisting of about 200,000 miniature windows. Astronomers can open and close these windows to allow light only from the galaxies they are interested in to pass through. This increases observation efficiency by more than 100 times compared to Hubble. Why is this so effective? Because with this, Webb can tell not only how bright or large a galaxy is, but also what it is made of. It can measure the amounts of elements like hydrogen, helium, oxygen, and carbon. It can even understand how fast these gases are moving and how hot they are. This not only proves the existence of those impossible galaxies in the early universe, but also allows us to understand how they matured so quickly chemically. But Sometimes, what you're looking for is not a bright galaxy, but the faint atmosphere of a planet in front of it. Or perhaps you want to see not the brightest, most chaotic center of a galaxy, but its faint, diffuse halo. This is where the fifth technique comes in, the light sculpting tools, coronagraphs, and integral field units. A coronagraph is like a small mask designed to block the light of a bright object at the center. It's just like using your hand to block the sun to see a fainter object next to it. The coronagraphs in Webb's NIRCam and MIRI instruments block the overwhelming glare of a star, allowing for the direct imaging of the much fainter exoplanets in its orbit. This technology is so sensitive that it can detect a planet that is 10 billion times fainter than the star itself. This is like trying to see a firefly flying next to a lighthouse. Integral field units, IFUs, solve a different problem. Instead of compressing an entire image into a single spectrum, IFUs slice the image into thousands of tiny pieces and create a separate spectrum for each piece. This creates a three-dimensional data cube of an object. 2 dimensions are spatial, up, down, left, right, and the third dimension is wavelength, color. This allows astronomers to simultaneously map the gas movements or changes in chemical composition in different regions of a galaxy. Hubble had very limited capabilities of this kind, but the IFUs in Webb's NIRSpec and MIRI instruments take this technique to a whole new level of sensitivity and resolution. Why is this so effective? Because these tools give us the power to see not just the big picture, but also the critical details within that picture. With all this incredible technology, Webb is located in a special orbit called the L2 point. This is a point about 1.5 million kilometers away from Earth, in the exact opposite direction of the Sunday. This is a kind of cosmic parking spot where the gravitational forces of the Sun, Earth, and Moon are balanced. This orbit allows Webb to gain 3 major advantages. First, its sun shield can always block these 3 heat sources at the same time, because the telescope can always keep its back turned to them. Second, this distance protects it from the infrared radiation, the heat emitted by the Earth itself. This helps the telescope maintain its incredibly cold temperatures. Third, the orbit at L2 allows the telescope to remain in a fixed position with relatively little fuel. This extends the life of the mission. Hubble, being in a close orbit to Earth, passes behind the planet every 90 minutes, which limits observation time and causes constant thermal changes. But Webb can perform 24/7 uninterrupted observations at L2. This is the key to how those incredible deep field images, which require very long exposures, are obtained. Webb's location is not just a preference, it is a strategic necessity that maximizes its scientific capabilities. From this distant, cold, and dark observation point, it can look into the deepest secrets of the universe. Infrared eyes, a giant mirror, an extremely cold environment, spectrographs that analyze light, masks that block glare, and a strategic orbit. C, I, 2, end, 2, I, 2, end, 2, I, C, I, C, 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 When all these technical marvels come together, they make the James Webb Space Telescope the most powerful observation tool in human history. We now know how the telescope works, the rewritten rules of the universe, and the first shocking findings that challenge these rules. But what is truly exciting is what it all means when these pieces come together. What do this technology and these findings bring us to the brink of one of the greatest mysteries of the universe? Could there be galaxies with different physical rules? Or even beyond that, could there be places where the very definition of life is completely different from what we know? Because in this new and strange universe that Webb is showing us, we may not just find new worlds, we may encounter structures that open the door to possibilities we can't even imagine, where physics itself works differently. Now, it is time to journey towards the most daring of these possibilities, towards the deepest secrets of the cosmos, because the climax starts now. And now, the climax, the real miracle. Because everything we've talked about so far was just a preparation, the quiet before a storm. What Webb showed us was not just a few anomalies that broke the rules. It made discoveries so profound, so shattering, that they force us to question the very fabric of reality itself. This is not just astronomy. This is about existence itself. There is no more room for medium tempo. There is no more time for calm explanations. Hold your breath. The climax begins now. Because the universe is nothing like we ever imagined. Here is the first epic moment. The most distant, oldest galaxy in history. It was impossible. Physically, it should not have been there. But Webb turned its eyes to the darkest corner of the universe, and it saw it. Its name is JADESGSZ130. This isn't just a code name. This is the place where history was rewritten. The light from this galaxy had been traveling to us for over 13.5 billion years. This means it's a photograph of a moment just 320 million years after the Big Bang. Only 2% of the universe's current age. This is the oldest galaxy ever observed in history, a record. But that's not the real shock. The real shock is that this baby galaxy was already shining with more than 1 billion stars. It took the Milky Way billions of years to reach this maturity, but this structure had managed it in the blink of a cosmic eye. Even more incredible, this galaxy was a full 100 times brighter than the largest galaxy our theoretical models predicted could exist at that time. This could not be an error. This meant throwing all our equations about the universe's formation speed into the trash. How could this be possible? How could so much gas come together in such a short time? How could so many stars ignite so quickly? Was the role of dark matter completely different from what we thought? When this discovery was published in the journal Nature Astronomy, it created an earthquake in the scientific world. Astronomers said, "We realized we have no idea what happened in the first 500 million years of the universe." This was like writing, "Here be monsters," on the edge of a map. But inside that monster, there was something even more terrifying. The second epic moment, the first quasar at the cosmic dawn, the brightest, most powerful object in history. A quasar is the light emitted by a supermassive black hole at its center, as it greedily devours the matter around it. They are the brightest lighthouses in the universe. But they too should not have existed in the early universe, because it took time for those giant black holes to form. Webb found a quasar from just 750 million years after the Big Bang. This in itself is a record, but the mass of that black hole exceeded all expectations. 1.6 billion times the mass of the Sunday. This was at least 10 times the theoretical maximum mass for that era. But the real impossibility was the mass of the galaxy it was devouring. The total stellar mass of the galaxy was almost the same as the mass of the black hole at its center. This ratio is something unseen in any galaxy in the modern universe. In today's galaxies, the central black hole makes up only 0.1% of the galaxy's total mass. But here, the ratio was close to 50%. This was like a mouse swallowing an elephant. How could this be possible? Did this show that black holes formed before galaxies, and that galaxies grew around them? Or were we looking at a completely new type of object called a direct collapse black hole, which so far only exists in theory? This discovery fundamentally shook the formation order of the universe's building blocks. Which came first, galaxies or the monster black holes? This question demolished one of the most fundamental pillars of cosmology. And then, the most incredible thing happened. Webb stopped looking just at matter. It saw something that challenged physics itself. The third epic moment, varying physical constants. This is the hardest one, but the most important. We believe that the laws of physics are the same everywhere in the universe. The gravitational constant, the speed of light, the fine structure constant. These numbers form the basis of reality. If even one of these constants were slightly different, the universe could not exist. But what if these constants change over time? Or even more shocking, what if they have different values in different parts of space? This is not science fiction. This is the most radical possibility pointed to by Webb's latest data. Webb analyzed the spectrum of light from very distant quasars, and it found the first tentative clues that this light interacted with a fine structure constant that was different, albeit by a very, very small amount from what we measure in modern laboratories. The difference is on the order of 1 part per billion, but if it's real, it changes everything. This could explain why those early galaxies grew so fast, because gravity might have been stronger back then. This could explain why those black holes fed so quickly, because the rules of matter-energy interaction might have been different. This is a possibility that requires us to rewrite not just our model of the universe, but physics itself. The scientific community is divided over this data. Some say it's a measurement error, others believe we are on the verge of a paradigm revolution, because if the laws of physics are not universal, then everything is possible. And this everything brings us to the fourth and final epic moment, the very definition of life. When Webb studied the atmosphere of a planet in the TRAPPIST-1 system, it didn't just look for water vapor or methane. It searched for the strangest, most unexpected chemical fingerprints of life, and what it found could change astrobiology forever. It discovered that the planet's atmosphere had 1,000 times less methane than expected, and almost no carbon dioxide. This means that a planet's atmosphere cannot be explained by any known geochemical model. How can this be possible? There seems to be only one answer: biology. But not the kind of biology we know. Perhaps on the planet's surface, there is an exotic metabolism that consumes methane and produces other gases we can't even imagine. Perhaps life doesn't even have to be carbon-based. Perhaps it's silicon-based, or uses a completely different chemistry. Webb didn't just show us an anomaly. It opened a window of possibility that pushes the limits of our imagination about what life could be. We are no longer just asking, is there water there? We are now asking, what chemistry is there, and what strange form of life does this chemistry feed? This is the first concrete evidence that the answer to humanity's oldest question, are we alone, might be much stranger and much more wonderful than we ever expected. The oldest galaxy in history, a black hole devouring its own galaxy, physical laws that might change, and the first potential whisper of a completely alien biology. These are the peak moments presented to us by the James Webb Space Telescope. Each one, on its own, is powerful enough to change the history of science. But when they all come together, they give us one single, shattering message. Everything we thought we knew about the universe was wrong. So, what does all this mean? What does this new, wild, and unpredictable universe tell us about our own origins and our future? Because these discoveries are not just about distant galaxies, they are about us. And the philosophical implications of this new reality are much deeper and more personal. Therefore, the philosophical implications of this new reality may be even more shattering than the scientific ones, because these discoveries are not just about distant galaxies. They are about us, about our place, our importance, our loneliness. This new story the universe is telling us fundamentally shakes the oldest stories we have told ourselves. We continue at maximum speed because there are more miracles to be understood. The fifth epic moment, the birth of unexpected order, creation in cosmic collisions, violence, chaos, destruction. This is how we imagined the early universe. But what if violence is also the engine of creation. Webb studied the collision of two giant galaxies, like the Antennae Galaxies. It should have been a catastrophe. The orbits of billions of stars were being torn apart. Gas clouds were being heated by shockwaves. But, Webb saw, for the first time in history, the birth of incredibly dense and orderly structures right in the heart of this chaos. Superstar clusters. Each one an incredibly dense ball containing millions of young, bright stars. These clusters were so dense that the distance between the stars inside them was 100,000 times less than the distance between our Sun and its nearest neighbor. One of these clusters packed 10 million stars into an area just 10 light-years wide. This is 1,000 times denser than even the most dense cluster in our entire galaxy. How could this be possible? The immense pressure created by the collision was compressing the gas so much that star formation was happening all at once, like an explosion. And these clusters were not just temporary, they were so massive that their gravity would hold them together, destined to become globular clusters in the future. This shows that some of the oldest and most enduring structures in the universe were born in the most chaotic moments. Destruction was, in fact, a process of creation. This discovery was like a cosmic echo of the punctuated equilibrium theory in evolutionary biology. Long periods of calm were interrupted by sudden and violent changes, and the greatest innovations emerged in these moments of chaos. Therefore, we understood that the universe not only grows, but also evolves in leaps during moments of crisis. But this creation was not limited to stars. It was also about planets. The sixth epic moment, the chemical secrets of planetary nurseries. We know how a planet is formed. In the disk of gas and dust around a star, particles come together, they grow, and eventually, they form a world. But the chemistry of that disk determines the fate of that planet. Will it have water? Will it have an atmosphere? Will it have the necessary elements for life? The answer to these questions was hidden in the innermost, hottest regions of the disk. And these regions were unobservable until now, due to the star's glare, consumes methane and produces other gases we can't even imagine. Perhaps life doesn't even have to be carbon-based. Perhaps it's silicon-based, or uses a completely different chemistry. Webb didn't just show us an anomaly. It opened a window of possibility that pushes the limits of our imagination about what life could be. We are no longer just asking, is there water there? We are now asking, what chemistry is there, and what strange form of life does this chemistry feed? This is the first concrete evidence that the answer to humanity's oldest question, are we alone, might be much stranger and much more wonderful than we ever expected. The oldest galaxy in history, a black hole devouring its own galaxy, physical laws that might change, and the first potential whisper of a completely alien biology. These are the peak moments presented to us by the James Webb Space Telescope. Each one, on its own, is powerful enough to change the history of science. But when they all come together, they give us one single, shattering message. Everything we thought we knew about the universe was wrong. So, what does all this mean? What does this new, wild, and unpredictable universe tell us about our own origins and our future? Because these discoveries are not just about distant galaxies, they are about us. And the philosophical implications of this new reality are much deeper and more personal. Therefore, the philosophical implications of this new reality may be even more shattering than the scientific ones, because these discoveries are not just about distant galaxies. They are about us, about our place, our importance, our loneliness. This new story the universe is telling us fundamentally shakes the oldest stories we have told ourselves. We continue at maximum speed because there are more miracles to be understood. The fifth epic moment, the birth of unexpected order, creation in cosmic collisions, violence, chaos, destruction. This is how we imagined the early universe. But what if violence is also the engine of creation? Webb studied the collision of two giant galaxies, like the Antennae Galaxies. It should have been a catastrophe. The orbits of billions of stars were being torn apart. gas clouds were being heated by shockwaves. But, Webb saw, for the first time in history, the birth of incredibly dense and orderly structures right in the heart of this chaos, superstar clusters. Each one an incredibly dense ball containing millions of young, bright stars. These clusters were so dense that the distance between the stars inside them was 100,000 times less than the distance between our Sun and its nearest neighbor. One of these clusters packed 10 million stars into an area just 10 light-years wide. This is 1,000 times denser than even the most dense cluster in our entire galaxy. How could this be possible? The immense pressure created by the collision was compressing the gas so much that star formation was happening all at once, like an explosion. And these clusters were not just temporary, they were so massive that their gravity would hold them together, destined to become globular clusters in the future. This shows that some of the oldest and most enduring structures in the universe were born in the most chaotic moments. Destruction was, in fact, a process of creation. This discovery was like a cosmic echo of the punctuated equilibrium theory in evolutionary biology. Long periods of calm were interrupted by sudden and violent changes, and the greatest innovations emerged in these moments of chaos. Therefore, we understood that the universe not only grows, but also evolves in leaps during moments of crisis. But this creation was not limited to stars. It was also about planets. The sixth epic moment, the chemical secrets of planetary nurseries. We know how a planet is formed. In the disk of gas and dust around a star, particles come together, they grow, and eventually, they form a world. But the chemistry of that disk determines the fate of that planet. Will it have water? Will it have an atmosphere? Will it have the necessary elements for life? The answer to these questions was hidden in the innermost, hottest regions of the disk, and these regions were unobservable until now due to the star's glare. But Webb looked there. Using NIRSpec, it chemically mapped the inside of the disk around a young star, just 150 light-years away, for the first time in history. And what it found changed all models of planet formation. In the disk, far beyond expectations, it found an incredibly rich and complex soup of organic molecules, not just water, carbon monoxide, carbon dioxide, hydrogen cyanide, and acetylene. These are the precursors to amino acids and other building blocks of life. The concentration of these molecules was 100 times greater than what theoretical models predicted. And this soup of life was well inside the snow line where planets form. How could this be possible? This meant that the basic components necessary for life were, by default, present from the very beginning, in exactly the right place as a planetary system forms. The chemistry of life is not an afterthought. It is an inherent process in planet formation. This could mean that the vast majority of rocky planets in the universe are born with all the basic chemical components necessary for life. This shows that the universe doesn't just permit life. Perhaps it encourages it. And if the chemistry of life is so common, then how diverse can life itself be? The seventh epic moment. Alternate worlds and the limits of imagination. Haitian worlds. This name may not mean anything to you, but it soon will. Because this could be the biggest revolution in the search for life. For years, we thought a habitable planet had to be like Earth, rocky, temperate, a thin atmosphere. But what if this is a limitation of our imagination? Astronomers theorized that a completely different type of planet could also be habitable. Haitian worlds. These are hot planets with a deep, global ocean covering the entire planet and a hydrogen-rich atmosphere. These planets are found in one of the most common planet sizes in the universe, between super-Earths and mini-Neptunes. Webb studied the atmosphere of a Haitian world candidate called K2, 18b, 120 light-years from us, and there it found not only water vapor, but also strong evidence of a molecule called dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by life, specifically by phytoplankton in the oceans. This is not definitive proof of life, not yet. 9. But, for the first time in history, we have found the trace of a chemical associated only with life, on a world completely different from our own. How could this be possible? This means that life might exist in a much wider range of conditions than we ever imagined. Perhaps life thrives in high-pressure, hydrogen-filled atmospheres, in conditions our biology could not withstand. This discovery has increased the number of types of habitable worlds we can search for by 10-fold, perhaps 100-fold. We are no longer just searching for second Earths. We are now searching for completely alien, completely new possibilities of life. The scientific world is literally holding its breath at the potential significance of this finding. Order born from chaos, the chemistry of life in the DNA of planets, and the whispers of potential life on worlds beyond our imagination. These discoveries show how creative, how efficient, and how surprising the universe is. They take us one step further, away from our cosmic loneliness. But now it is time to slow down for a moment from this dizzying pace. Time to stop and think. Because all these incredible findings, these records, these demolished theories, point to a single, deep question. So, what does all this new knowledge mean for us as a species? In this vast, strange, and perhaps life-filled universe, where exactly is humanity's place? Because the answer to this question is not in telescopes or equations. It lies within us, in our own consciousness. And confronting this answer may be even harder than finding the most distant galaxy in the universe. And now we ask ourselves, after all this dizzying speed, these record-breaking discoveries and demolished theories, we stop and take a breath for a moment. Because we now face the most important question. What does all this new knowledge, this vast, strange, and perhaps life-filled universe mean for us as a species? In this cosmic ocean, where exactly is humanity's place? Because the answer to this question is not in telescopes or equations. It lies within us, in our own consciousness. And confronting this answer may be even harder than finding the most distant galaxy in the universe. Because this means confronting the greatest paradoxes in human history. Here is the first and most overwhelming paradox, the scale paradox. On one hand, you have the unimaginable size of the observable universe, spanning 93 billion light-years, and the 2 trillion galaxies within it, because these numbers represent a scale beyond even our wildest dreams. On the other hand, there is you, and a consciousness trapped in an incredibly fragile body, about 1.7 meters tall, made of carbon and water, on the surface of a pale blue dot, revolving in orbit of a small star in a quiet suburb of the Milky Way galaxy. How can these two scales coexist? How can such a massive structure allow for the existence of such a tiny witness? There is a tragic truth to this question. It is our physical limitation and our cosmic insignificance. When the light from the galaxy JADESGSZ130 reached us, that galaxy was no longer there. Perhaps it has long since merged with another galaxy or been swallowed by a black hole. We will never go there. Even if we traveled at the speed of light, it would take us 13.5 billion years to get there. That's longer than the current age of the universe. We are like a visitor looking at the most precious artifact in a museum, but knowing we can never touch it. This vast universe is not our playground. It is an eternal display case for us. And as we look through the glass of this display case, we are confronted with the reality of how small, how slow, and how powerless we are. This is humanity's deepest sorrow in the face of the universe. But within this same paradox, an incredibly beautiful truth is also hidden. That 1.7 meter body, that fragile consciousness, may be the only thing capable of comprehending the 93 billion light-year expanse of the universe. The universe itself may be large, but it is not aware that it is large. Those galaxies shine, but they do not know why they shine. Those black holes devour, but they do not understand what they devour. But you understand. You are a tool the universe created to think about itself. You may be physically small, but you are mentally limitless. The 100 billion neurons in your brain are almost the same number as the galaxies in the universe. And these neurons possess something that even the universe itself does not have: curiosity, the desire to understand. Therefore, yes, we may be small, but we are also the place where the universe gains meaning. You too live in the middle of this contradiction. Every day, you deal with small problems in your own small world. But when you stop for a moment and look at the sky, you feel that you are a part of that infinity. You are both a speck of dust and a universe. The head you carry on your shoulders is the most complex structure in the universe, capable of making sense of the data collected by the James Webb Telescope. Therefore, do not be ashamed of your smallness, because your existence gives this vast and silent universe a voice, a meaning, and a purpose. And this brings us to a second, more personal paradox, the time paradox. On one hand, there is a cosmic epic that has been going on for 13.8 billion years, a nearly infinite ocean of time where stars are born and die, galaxies collide, and the universe slowly evolves. On the other hand, there is your short, precious life, maybe 80 years, maybe 90. On the cosmic calendar, this duration is less than the blink of an eye. The entire written history of humanity, about 5,000 years, is only 3/100,000ths of the universe's age. How can these two timescales come together? There is a tragic side to this question as well. It is our transience. We are extras who appear on this cosmic stage for just a moment and then disappear forever. We did not see the beginning of the universe, and we will most likely not see its end. In this short time given to us, we can only see a small fraction of the universe's secrets. We will never know what the universe will look like billions of years from now, what new life forms will emerge, or what new levels of consciousness will be reached. This is like reading only a single page of a book and never being able to learn the rest. This is the most fundamental pain of existence, the conflict between the desire to know and the limits of a lifetime. And yet, there is a miraculous beauty in this fleeting moment, because what matters is not how long we live, but what we are in that brief moment. You are the latest, most advanced product of a 13.8 billion year evolutionary process. Every single atom in your body was forged in the heart of a star billions of years ago. You are literally made of stardust. And this brief moment of consciousness given to you is the moment when that stardust stood up and questioned its own origin. This is the most magical moment of the universe. Maybe we don't live forever, but in this short time, we become the universe itself. The universe that is aware, that feels, that loves, and that wonders. Therefore, yes, our time may be limited, but this limited time is the most precious moment of the universe. You are right in the middle of this moment. Your every breath is a part of this 13.8 billion year story. You are the legacy of all the stars of the past and the seed of all the possibilities of the future. This short life is not a punishment, but a gift. It is the chance the universe has given you to experience itself. Therefore, do not waste this moment, because you are in that brief, priceless moment when the universe is awake. These paradoxes of scale and time lead us to another, deeper thought, perhaps the most fundamental philosophical problem of humanity. And this problem, in this new, strange universe that Webb has shown us, we now know operates under completely different rules. Therefore, the paradoxes of scale and time bring us to humanity's most fundamental philosophical problem, the third great contradiction, the loneliness and connection paradox. On one hand, there is this universe that Webb has shown us, trillions of galaxies, hundreds of billions of stars in each, and an uncountable number of planets orbiting these stars. Statistically, it seems almost inevitable that life is widespread. Perhaps right now, as we speak, on thousands, even millions of different worlds, different biologies, different consciousnesses are being born, living, and dying. This creates a sense of a cosmic crowd. On the other hand, there is the deafening silence of the Fermi paradox. If the universe is so crowded, then where is everybody? This is the expression of our deepest cosmic loneliness. How can these two truths, the existence of so many potential neighbors and the complete lack of any evidence for their existence, be true at the same time? There is a tragic truth to this question. It is the cruelty of distance and time. Perhaps the universe is indeed full of life, but the average distance between civilizations could be hundreds of thousands of light years. This means that two neighbors may be aware of each other's existence, but they can never offer each other a cup of coffee or even call out to each other. Perhaps civilizations, just like ours, can only exist for a few thousand years before they destroy themselves. In that case, the universe is like a forest filled with countless fireflies that blink on at different times and can never see each other. This is the most painful kind of loneliness. Loneliness in a crowd. To be provably alone in a potentially full universe. This is our current situation. But in this silence, a different and deeper idea of connection is born. Perhaps we cannot communicate directly with other civilizations, but we are connected to them through the language of the universe itself, the laws of physics. The potential life on that distant Haitian world is made of the same hydrogen atoms, the same carbon atoms as us. The gravity that holds them together is the same that holds us on our planet. The fusion that ignites their star is the same that makes our sun shine. This is a universal brotherhood, not biological, but chemical, physical. We are players in different parts of the universe, playing by the same fundamental rules, made of the same basic materials. Therefore, when we look at the sky and hear the silence, it is not the silence of a void. It may be the silence of our distant relatives, and this alleviates our loneliness, even if just a little. You are a living proof of this connection. The iron in your body came from a supernova that exploded billions of years ago. The oxygen in your lungs was the last breath of a star. You are the assembly of pieces from different corners of the universe, come together on this planet, in this body, in this consciousness. You are not just an individual. You are a cosmic collection, and this is your deepest connection. You are not alone, because the universe itself is inside you. These contradictions, to be huge yet small, infinite yet brief, lonely yet connected, confront us with the most fundamental questions about what it means to be human. And after learning this new information about this strange universe, how do you feel? On one hand, is there a sense of awe and perhaps fear in the face of the universe's unimaginable size and our insignificance? On the other hand, is there a sense of pride and wonder that you possess the consciousness capable of understanding this massive structure? The answer is that both are true. Because to be human is to live in the tension between precisely these two feelings. We are both the kings of the universe because we can understand it, and its most powerless slaves because we are subject to its rules. Accepting this tension is the first step to understanding our own place. We now know that our scale is insignificant, but our consciousness is worth everything. We understand that our time is short, but this moment is the most precious moment of the universe. And perhaps we are cosmically alone, but at the most fundamental level, we are inseparably connected to the universe itself and everything within it. These philosophical truths are as important as the data presented to us by the James Webb Telescope, because they show us what this knowledge means for us, what kind of responsibility it places upon us. But after all this inward journey, one more question remains, perhaps the most important one. If the rules of the universe are different than we thought, if life is much more common and diverse than we imagined, and if we are both the smallest and the most meaningful part of this vast structure, then what will we do with this knowledge? How should this new cosmic perspective shape our future, our behavior as a species, and our purpose in the universe? Because this is not just a journey of discovery, it is also a journey about humanity's next step. And what that step will be is entirely in our hands. Therefore, the question of what we will do with this new cosmic perspective leads us to a deeper, more internal layer, to the contradictions at the very core of the human condition. This is not just about what we know, but about who we are, because every new truth we learn about the universe also illuminates a truth about ourselves. And this illumination can sometimes be unsettling and sometimes incredibly liberating. Now is the time to ask these most internal questions. Here is the fourth, and perhaps most modern paradox, the knowledge and action paradox. On one hand, we have an incredible wealth of knowledge thanks to tools like the James Webb Telescope. We can see the most distant corners of the universe, count the molecules in a planet's atmosphere, and analyze a time just 300 million years after the Big Bang. Never in human history have we known so much, with such great certainty. This is the greatest triumph of our collective intelligence and curiosity. On the other hand, there is our astonishing inability to turn this knowledge into meaningful action. This is about our own planet, our own pale blue dot. We understand our cosmic rarity, our fragility, but still, we do not strive enough to protect it. How can these two states coexist? How can we be both so wise and so foolish? There is a tragic truth to this question. It is that knowledge, by itself, is not enough for behavioral change. Understanding a problem intellectually is not the same as creating the emotional and collective will required to solve it. Decades have passed since Carl Sagan published his pale blue dot photograph. That photo showed the loneliness and unity of our planet in the universe in the most poignant way. But since then, our divisions on our planet have deepened. Our ecological crisis has worsened. It is as if the more we understand the vastness of the universe, the more we sink into our own little problems. This is humanity's greatest irony: to have the intelligence to conquer the universe, but to be incapable of managing our own home. But within this tragedy, there is also a hopeful beauty, because this knowledge offers us a choice, a roadmap. In the past, ignorance could have been a reason for our inaction, but not anymore. Now we know. Every new impossible galaxy web shows us. Every new potentially life-bearing world serves as a mirror, reminding us how precious our own world is. This knowledge is not an accusation, but an invitation. It invites us to be better, to act more wisely, because when we understand how full the universe is, we confront our own emptiness. And this confrontation is where real change can begin. Therefore, knowledge is not a burden, but a lever that can lift us to a higher level of consciousness. You are a part of this choice. Every day, you try to strike a balance between these great cosmic truths you learn and the small, personal truths you live. You are part of both the problem and the potential solution. Will you see this knowledge as a source of despair or as a source of inspiration? This is not a decision that only scientists or leaders have to make. This is a decision that all of us, each and every one of us, must make. Because the universe has set the stage for us. But how we play the game is up to us. And this brings us to the fifth and most personal paradox, the meaning and meaninglessness paradox. On one hand, there is the reality of a completely materialistic universe, laws of physics, chemical reactions, random mutations. From this perspective, the universe has no intrinsic purpose or meaning. It just is. We too are complex biochemical accidents within this vast, purposeless machine. Our lives, our joys, our sorrows, all are ultimately meaningless whispers that will fade away in a cosmic noise. On the other hand, There is these accidents, insatiable, irresistible urge to search for meaning. We create art, we fall in love, we do philosophy, we question the origin of the universe. How can this be possible? How can a purposeless universe create meaning-seeking beings? The tragic side of this question is that the ultimate, universal meaning we seek may not exist at all. Perhaps the universe has no answer to give us. Perhaps the answer to the question, why are we here, is for no reason. This is an unbearable thought for many people, because this means there is a void at the foundation of existence. This could mean that all our efforts, all our achievements, are ultimately steps taken towards nothingness. This is the deepest existential fear. But once again, we find the deepest meaning in the heart of this meaninglessness. Because if there is no ready-made meaning offered to us by the universe, it means we are free to create our own meaning. This is the greatest gift. We are the universe's blank canvas, and the brush is in our hands. Meaning is not something discovered. It is something invented. It exists in your actions, your relationships, your curiosity, your compassion. The universe may not have a purpose, but you can have a purpose. And this is the greatest gift you can bestow upon the universe. Therefore, meaninglessness is not a curse, but a freedom. The void is not something to be feared, but an opportunity to be filled. You too create your own meaning every day. When you wake up in the morning, when you choose what to do that day, when you help someone else, when you learn something new, you are adding meaning to the universe. You are the poet of this vast, silent universe. And every line you write, no matter how small, makes the universe a less meaningless place. Your existence is the meaning the universe gives to itself. These deep contradictions, that delicate balance between knowledge and inaction, meaning and meaninglessness, bring us to the essence of being human. We are beings full of contradictions. Our potential is infinite, but our limits are painfully real. But after all these thoughts, after all this philosophical depth, as we approach the end of our journey, perhaps there is one more truth that unites all these paradoxes, that transcends them all. And this truth is not just about us or the universe. It is about the mysterious, indescribable relationship between the two. And this final layer depends entirely on our perspective, our curiosity, and our courage. Therefore, this final philosophical layer is perhaps the most difficult, because it is not about the universe out there, but the universe inside, our own mind. This is the paradox of curiosity and acceptance. On one hand, there is the fundamental driving force that moves the human species forward, curiosity. The questions, why, how, what else is there? These questions brought us out of caves, enabled us to cross oceans, and now have us looking at the stars. The James Webb Telescope is the latest and most magnificent monument to this curiosity. It is a physical manifestation of our desire to push the boundaries of knowledge. On the other hand, we must face the fact that the universe will not always give us the answers we seek. Some questions may never be answered. Some mysteries may remain mysteries forever. How can these two states coexist? How can we both burn with the desire to know everything and accept the fact that we will never know everything? There is a tragic truth to this question. It is that our curiosity will always be one step behind the complexity of the universe. Every new answer gives birth to 10 new questions. Webb showed us the first galaxies, but now we wonder what is inside those galaxies. What came before them? Webb showed us exoplanet atmospheres, but now we wonder what is swimming in the oceans beneath those atmospheres. This is a quest that will never end, and this can lead to a kind of fatigue, a kind of sorrow, because if the destination can never be reached, what is the point of running? This is the myth of Sisyphus, cursed forever to push the boulder up the hill, only to watch it roll back down again. The scientific quest can sometimes feel like this, but within this endless quest lies the deepest beauty and hope. Because what matters is not reaching the destination, but the journey itself. Curiosity is not a destination, but a way of being. What makes us human is not finding the answers, but asking the questions. And every new question expands our universe a little more, stretches our minds a little further. Therefore, yes, perhaps we will never find the theory of everything. But during this quest, we learn so much about ourselves, about each other, and about this magnificent universe that the journey itself becomes the greatest reward. Acceptance is not a defeat, but a wisdom. Accepting the limits of our knowledge does not diminish the value of our curiosity. On the contrary, it makes it even more precious, because it allows us to understand how small and valuable an island everything we know is in that infinite ocean of the unknown. You are a part of this journey. In your own life, you have your own curiosities, your own unanswered questions. You too live with both the power that knowledge gives and the humility that not knowing brings. And finding this balance is necessary not just to be a scientist, but to be a complete human being. Keep wondering, never stop asking questions. But also know that you don't have to solve all the universe's secrets. Sometimes it is enough to just stand in awe of the beauty of that mystery. And this brings us to the final, most integrative paradox, the fragility and resilience paradox. On one hand, there is the fact of how fragile we are, both as individuals and as a species. An asteroid, a pandemic, a climate change. Our existence hangs by a cosmic thread. The James Webb Telescope reminds us of this fragility every day. It shows us how big, how indifferent, and sometimes how dangerous the universe can be. On the other hand, there is the incredible resilience of life itself. It has survived on this planet for 4 billion years through 5 major mass extinctions, spreading everywhere from the deepest ocean trenches to the highest mountain peaks. And now, that life is reaching out into space, looking at other worlds. How can this be possible? How can we be both so fragile and so resilient? The tragic side of this question is that our fragility will always exist. No matter how much technology we develop, no matter how much we learn, we will always remain small in the face of the universe's forces. This is a hard truth to face, because it means accepting that security is an illusion, that control is not always in our hands. This is the fundamental uncertainty of existence. But within this fragility, we find our greatest strength. Because what makes us resilient is not that we are invincible, but our ability to adapt, our capacity to change, to learn, and to find a way even in the most difficult conditions. Life survives not because it is armored, but because it is flexible. And human consciousness is the extreme point of this flexibility. We can evolve not just genetically, but culturally. We can pass on ideas, stories, knowledge through generations. This is our superpower, and the James Webb Telescope is the latest example of this power. It is the result of thousands of people coming together over decades, working to overcome one of humanity's greatest challenges. It is a symbol of our collective resilience. You are a part of this story. In your own life, you face your own challenges, your own fragilities. But at the same time, you carry within you an incredible resilience that comes from billions of years of evolution. You are descended from survivors, and this gives you the strength to overcome any kind of difficulty. Do not be afraid of your fragility, because it makes you human. But never forget your resilience, because it keeps you alive. And so, we approach the end of this long and deep journey. We have traveled from the farthest corners of the universe to the deepest layers of our own consciousness. We have faced our smallness and our greatness, our short lives and our eternal legacy, our loneliness and our deep connections. We have seen the power of our knowledge and the danger of our inaction. We have taken on the responsibility of creating our own meaning in a meaningless universe. We have understood the infinity of our curiosity and the wisdom of acceptance. And finally, we have realized that our deepest fragility is the source of our greatest resilience. Now we know the universe is not just a place, it is a mirror. And when we look into that mirror, what we see is not just stars and galaxies. What we see is ourselves, with all our contradictions, with all our beauty, with all our potential. And this journey has given us one clear message. In this journey, we have challenged everything we knew about the universe. But I didn't tell you that we can not only see the universe, but also hear it. When two black holes merge, they create ripples in space-time itself, just like a stone thrown into a lake.